All right, continuing onward with chapter 19. This is my web browser. Cool. Next section is advanced traits, which is 19.2. We first covered traits in the traits defining shared behavior section of chapter 10. But as with lifetimes, we didn't discuss the more advanced details. Now that you know more about Rust, we can get into the nitty-gritty. Ooh. Okay. Specifying placeholder types in trait definitions with associated types. That kind of sounds like default values to me. I don't know what that sounds like to you, but to me that sounds like default values. Associated types connect a type placeholder with a trait such that the trait method definitions can use these placeholder types in their signatures. The implementer of a trait will specify the concrete type to be used in this type's place for the particular implementation. That way, we can define a trait that uses some types without needing to know exactly what those types are until the trait is implemented. We describe most of the advanced features in this chapter as being rarely needed. Associated types are somewhere in the middle. They are used more rarely than features explained in the rest of the book, but more commonly than many of the other features discussed in this chapter. One example of a trait with an associative type is the iterator trait that the standard library provides. The associated type is named item and stands in for the type of the value the type implementing the iterator trait is iterating over. In the iterator trait and the next method section of chapter 13, we mentioned that the definition of iterator trait is as shown in listing 19-12. This thing. Public trait iterator. Here's the type, associative types, and we're returning the option of that associated type. Self that item, that type. So yeah, I read this first paragraph. That didn't really make sense to me. This down here makes a lot more sense to me. They're seemingly just talking about this thing, the type that's associated with this trait. Okay. The type item is a placeholder type, and the next method's definition shows that it will return values of type option self item. Implementors of the iterator trait will specify the concrete type for item, and the next method will return an option containing a value of that concrete type. So based on what they're saying here, it seems as though, yes, this is a placeholder, and it is the responsibility of the person implementing this trait to specify what item is, or like what type it should be. And then next is just going to return that type. So not necessarily a default value, but a placeholder. Associative types might seem like a similar concept to generics, in that the latter allows us to define a function without specifying what type it can handle. So why use associated types? Okay, that's a valid question. So they're stating here that this, as described so far, is similar to generics, as in the type isn't defined until like when we're using it, until we want to like run it. So why not use generic types? So let's see why they use associated types. Let's examine the difference between the two concepts with an example from chapter 13 that implements the iterator trait on the counter struct. In listing 13-21, we specify that the item type was U32. Here's a counter. We specified the type is going to be U32, and then we just continued on with it. This syntax seems comparable to that of generics, so why not just define the iterator trait with generics, as shown in listing 19-13. Option T. The difference is that when using generics, as in listing 19-13, we must annotate the types in each implementation because we can also implement iterator string for counter or any other type. We could have multiple implementations of iterator for counter. In other words, when a trait has a generic parameter, it can be implemented for a type multiple times, changing the concrete types of the generic parameter each time. When we use the next method on counter, we would have to provide type annotations to indicate which implementations of iterator we want to use. With associated types, we don't need to annotate types because we can't implement a trait on a type multiple times. In listing 19-12, with the definition that uses associated types, we can only choose what the type of item will be once, because there can only be one implement iterator for counter. We don't have to specify that we want an iterator of U32 values everywhere that we call next on counter. I think I get it. So if we were to use a generic, then one generic, you can pass in any type, and then you have to adhere to that type for the entirety of using it. But then you also have to note when you're calling the iterator, you have to pass in something to let the iterator know what type of iterator you want, because the generic's gonna like create a new iterator for each type, right? Because that's how it like flattens out compiler wise. In my mind, that would seemingly work, but it's also seemingly convoluted. So yeah, associative types, I can understand why they would use it. It is kind of simple just to write this thing, and then you don't have to worry about any referencing or which iterator you're using. It's pretty explicit. But their use case for not using generators, I'm not sure if I completely understand it. They also state here that when we use the next method on counter, we would have to provide type annotations to indicate which implementation of iterator we want to use. I'm not sure if they mean like on each next call, or if you're just iterating over it once, because if you're using a for loop, then something under the hood to probably do it for you. In any case, that's not an option, so we can just move on. Default generic type parameters and operator overloading. When we use generic type parameters, we can specify a default concrete type for the generic type. This eliminates the need for implementors of the trait to specify a concrete type if the default type works. The syntax for specifying a default type for a generic type is placeholder equal concrete type when declaring the generic type. A great example of a situation where this technique is useful is with operator overloading. Operator overloading is customizing the behavior of an operator, such as plus, in particular situations. Rust doesn't allow you to create your own operators or overload arbitrary operators, but you can overload the operations and corresponding traits listed in standard library ops by implementing the traits associated with the operator. For example, in listing 19-14, we overload the plus operator to add 2 point instances together. We do this by implementing the add trait on the point struct. Okay, so they're trying to give us an example of when to use the syntax for the placeholder and concrete type. And they say the example that they're going to use involves operator overloading, which it doesn't seem like you can do for the most part. It seems like you can have a struct, and then within the struct you can define how add should work, which I guess is technically overloading. Anyway, let's see what they have here. So we have standard library ops add, the trait for adding. We create our struct. We have debug, so we could like print it out easily. We have parcel equal, so we don't have to write out all of the equivalencies for, I guess, doing math on it. And then we have implement add for point. We have the type output point. So I guess this is the placeholder. And then we have function add other point. And we can do self x plus other x. This can come in as other. And then self y plus other y. And we return, this is returning a new point instance. and then we can do the assertion here that it works. So yeah, so I have no doubt that this works. This is pretty straightforward. I guess my question is this what they wanted to show us? Is that the placeholder type equals concrete type? Probably. The add method adds the x values of 2-point indices and the y value of 2-point indices to create a new point. The add trait has an associated type named output that determines the type returned from the add method. The default generic type in this code is within the add trait. Here's the definition. Trait add right hand side self type output add whatever the right hand side is, which is self, and self that output, which is here. Okay. This code looks generally familiar. A trait with one method and an associated type. The new part of right hand side equals self. This syntax is called default type parameters. The right hand side generic type parameter, I keep saying right hand side, it's RHS, but it's short for right hand side, that's why I keep saying it. So the RHS generic type parameter is short for right hand side, defines the type of the right hand side parameter in the add method. If we don't specify a concrete type for right hand side, when we implement the add trait, the type of right hand side will default to self, which will be the type we're implementing add on. I see, so it is a default parameter. Okay, cool. So in this trait, we have add. We define that the right hand side of the add by default should be self, but if we wanted to, we could change the right hand side to something else. Just by default, it's going to be self. So if we don't specify it, then the right hand side has to be equal to whatever the left hand side is. When we implement add for point, we use the default for right hand side because we wanted to add 2-point instances. Let's look at an example of implementing the add trait where we want to customize the right hand side type rather than using the default. And then this is probably going to be example. We have two structs, millimeter and meters, holding values in different units. We want to add values in millimeters to the values in meters and have the implementation of add do the conversion correctly. We can implement add for millimeters with meters as the right hand side as shown in listing. Here we go. So the example is we're just adding two different units, and I guess we're just going to account for like the conversion within the add. So we have our struct for millimeters, which is U32. We have our struct for meters, which is U32. And then we want to implement add for millimeters. The output is going to be millimeters. Here we state that the other is going to be meters and that we're returning meters, self.0, which is like a tuple of 1, other.0 times, we're doing the conversion. Okay, oh, here we go. Here's the right hand side specification. This is what I missed. Add, implement add, and this is what we define what the right hand side is going to be. Cool. That makes sense. I'll keep that in view. To add millimeters to meters, we specify implement add meters to set the value of the right hand side type parameter instead of using the default of self. That makes complete sense. Cool. You'll use the default type parameter in two main ways: to extend a type without breaking existing code, to allow customizations in specific cases most users won't need. The standard library's add trait is an example of the second purpose. Usually, you'll add two like types, but the add trait provides the ability to customize beyond that. Using a default type parameter in the add trait definition means you don't have to specify the extra parameter most of the time. In other words, a bit of implementation boilerplate isn't needed, making it easier to use the trait. The first purpose is similar to the second purpose, but in reverse. If you want to add a type parameter to an existing trait, you can give it a default to allow extensions of the functionality of the trait without breaking the existing implementation code. I'm not exactly sure if I understood the first one. Like, the second one makes sense to me. It's allowing customization in specific cases, adding millimeters to meters. That's exactly that. But extending a type without breaking existing code for an operator, is that like changing add in such a way that it does something else as well? I mean, yes, you can technically extend it using this method, I guess. I'm having a hard time thinking about why I would want to. But okay. Fully qualified syntax for disambiguation, calling methods with the same name. Oh. Nothing in Rust prevents a trait from having a method with the same name as another trait's method, nor does Rust prevent you from implementing both traits on one type. It's also possible to implement a method directly on the type with the same name as methods from traits. When calling methods with the same name, you need to tell Rust which one you want to use. Consider the code in listing 19-16, where we've defined two traits, pilot and wizard, that both have a method called fly. We then implement both traits on a type human that already has a method named fly implemented on it. Each fly method does something different. Okay, so here we're going to learn how to distinguish between ambiguous names, because if the pilot can fly, which is a trait, and wizard can fly, and the human can fly, and the human, uses the traits, or the pilot and wizard traits are implemented on human, then things can get hairy. So let's see what happens. So we have the trait pilot. We have the one method fly. Same thing for wizard. We have a struct that's a human. We implement fly for human. We implement pilot for human, which has to implement fly because that's here. We implement wizard for human, which also has to implement fly because that's here. And then we call human fly. And we implement fly on human, as in the human section we have another version of fly. So we have 1, 2, 3 versions of fly for the struct human. So when you call the method fly on a human, which one are you calling? When we call fly on an instance of human, the compiler defaults to calling the method that is directly implemented on the type, as shown in listing 19-7. Okay, so by default it calls the human one, because that's the type. We have a struct that is human, and that is the closest association in terms of the method called fly. That makes sense. Running this code will print waving arms furiously, showing that Rust called the fly method implemented on human directly. To call the fly methods from either the pilot trait or the wizard trait, we need to use more explicit syntax to specify which fly method we mean. Listing 19-8 demonstrates the syntax. I see. Pilot, : fly, and then we pass in a reference to the person. And same thing for wizard. Okay, so if the method, let's assume all these methods have the same name, because they do in this case, fly. If you want to distinguish them, then you have to call it using like the trait itself reference. So the trait is wizard, the method on the trait is fly, and then you pass in person as the reference, which then we'll call that fly. That makes sense. Specifying the trait name before the method name clarifies to Rust which implementation of fly we want to call. We could also write human : fly and pass in our reference to person, which is equivalent to the person.fly that we used in listing 19-18, but this is a bit long to write if you don't need to disambiguate. Running this code will print the following. This is your captain speaking, up, waving arms furiously. Because the fly method takes a self parameter, if we had two types that both implement one trait, Rust could figure out which implementation of a trait to use based on the type of self. However, associated functions that are part of traits don't have a self parameter. When two types in the same scope implement that trait, Rust can't figure out which type you mean unless you use fully qualified syntax. For example, the animal trait in listing 19-19 has the associated function baby name, the implementation of animal for the struct dog, and the associated function baby name defined on dog directly. I'm not exactly sure what I just read. Let me look at this real quick. So actually, let me go back up. So here they mention fully qualified syntax. So in the cases where Rust doesn't know which one you called, like how to distinguish between fly, fly, and fly, then you have to use the fully qualified syntax, which is seemingly this. And if we go back here, we see that fly does take a reference of self. So as long as you pass in the reference, here we go, then this should work. And this also works with human, : fly. They're all written the same way. So that makes sense. Oh, I think what they're stating here is that if there were other types associated with it, like self is going to reference a type, right? And if there were like one type that did one type of fly and another type that did another type of fly, then the compiler would be able to distinguish. But down here, we have, let's see, we have trait, animal, function, baby name, string, struct dog, dog implements baby name, animal for dog, baby name, baby name. So without going down here first, based on reading and everything we just looked at, I would assume, wait, this doesn't have self. Self is no longer here. I don't know which one is being called, actually. This code is used for animal shelters that want to name all puppies Spot, which is implemented in the baby name associated function that is defined on dog. The dog type also implements the trait animal, which describes characteristics that all animals have. Baby dogs are called puppies, and that is expressed in the implementation of the animal trait on dog in the baby name function associated with the animal trait. In main, we call dog baby name function, which calls the associated function defined on dog directly. This code prints the following. A baby dog is called Spot. Okay, so they're saying for this code here, which I could just run this just to verify, but more or less it's going to print that the dog's name is Spot, and Spot comes from this implementation, the one that's directly associated with dog, which is the struct. That makes sense. That output isn't what we wanted. We want to call the baby name function that is part of the animal trait that we implemented on dog. So the code prints a baby dog is called a puppy. The technique of specifying the trait name that we used in listing 19-18 doesn't help here. If we change main to the code in listing 19-20, we'll get a compilation error. Okay, so I'm starting to understand what they're trying to show us. So here, I noted earlier that we don't use self. And because we don't use self, something like this wouldn't work because we don't pass in a reference to anything here. We should get a compilation error. Because animal baby is an associated function rather than a method, and thus doesn't have a self parameter. Rust can figure out which implementation of animal baby we want. We'll get this compiler error. Type annotation required, cannot resolve animal, baby. To disambiguate and tell Rust that we want to use the implementation of animal for dog, we need to use fully qualified syntax. Listing 19-21 demonstrates how to use fully qualified syntax. Oh, so I was wrong earlier. Fully qualified syntax might also include this. Well, at least in this case, since there is no self. We want the dog as animal implementation of baby name, and then that should work. And we could test that out. Move you over. A baby dog is called a puppy. That did work. So this syntax is what we want, which is referencing seemingly this right here. Okay. We're providing Rust with a type annotation within the angle brackets, which indicates we want to call the baby name method from the animal trait as implemented on dog by saying that we want to treat the dog type as an animal for this function call. This code will now print what we want. A baby dog is called a puppy. In general, fully qualified syntax is defined as follows. They could have led with this, but okay. Fully qualified syntax. Type as trait. Function, receiver, if method, next arg. Okay, so the type, dog, as trait, the trait is animal, and then the function is baby name, and we don't have any, nothing to pass into the function, so we're good here. For associated functions, there will not be a receiver. There would only be a list of other arguments. You could use fully qualified syntax everywhere that you call functions or methods. However, you're allowed to omit any part of the syntax that Rust can figure out from other information in the program. You only need to use this more verbose syntax in cases where there are multiple implementations that use the same name and Rust needs help to identify which implementation you want to call. That makes sense. Using super traits to require one trait's functionality within another trait. That sounds like nested traits. Okay. Sometimes you might need one trait to use another trait's functionality. In this case, you need to rely on the dependent trait also being implemented. The trait you rely on is a super trait of the trait you're implementing. For example, let's say we want to make an OutlinePrint trait with an OutlinePrint method that will print a value framed in asterisks. So we want to create this thing, which I think I attempted to do at one point in time and failed. So I'm kind of curious to see how they go about doing this. Continue from here. That is, given a point struct that implements display to result in x, y when we call OutlinePrint. For example, let's say we want to make an OutlinePrint trait with an OutlinePrint method that will print a value framed in asterisks. That is, given a point struct that implements display to return in xy, when we call OutlinePrint on a point instance that has 1 for x and 3 for y, it should print the following. This thing. So just for clarity's sake, they're saying that we have an OutlinePrint trait that has this method on it, and we already have a struct that is called point that implements display, and display results in this xy. But when we call OutlinePrint, we want point instance to display this. And this is an example when x is 1 and y is 3. In the implementation of OutlinePrint, we want to use the display traits functionality. Therefore, we need to specify that the outline print will only work for types that also implement display and provide the functionality that outline print needs. You can do that in the trait definition by specifying outline print display. This technique is similar to adding a trait bound to the trait. Listing 19-22 shows an implementation of the outline print trait. Okay. So they're saying using this syntax, we have the trait, and then putting the trait that we want our trait to use within it here, which I thought was covered in the trait bounds thing, but this might be slightly different. I guess syntactically it might be different. So with trait bound, if I recall correctly, we were saying that the item that you're using that you're implementing this trait on has to have trait 1 and trait 2, as in they're like bounded together. But this is sort of saying that anything that implements this trait, this trait will use the functionality of the other trait. So I guess that is different. Yeah, that makes sense. So looking at the implementation, we have OutlinePrint, output self.TwoString. Maybe this is the display portion of it. We get the length, and we then just format everything else. That sort of makes sense, but at the same time, if the characters, like we did it with single digits, but if it's double digits, I don't think this is going to work out well. Moving onward, we can test that a little later. Because we've specified that OutlinePrint requires the display trait, we can use the TwoString function that is automatically implemented for any type that implements display. If we try to use TwoString without adding a colon and specifying the display trait after the trait name, we will get an error saying that no method name TwoString was found for the type self in the current scope. So yeah, I was right. So the difference between bounds and what this is, and this is, what is this called? Super traits, is that if we specify it in this manner, within this trait, we can use the functionality of this trait, and that was the TwoString. Let's see what happens when we try to implement OutlinePrint on a type that doesn't implement display, such as the point struct. Here's the point, here's the OutlinePrint. We get an error saying that display is required but not implemented. Here we go. Standard display not satisfied. Point can't be formatted with the default formatter. Try using blah 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 instead. Help, the trait display is not implemented for point. So this is the line that we really care about, the help. So to fix this, we implement display on point and satisfy the constraint that OutlinePrint requires, like so. And here it is. Here's the display, here's the point, and then the format, which I guess is the only function that needs to be satisfied for this trait, and writing it out. So there was a lot of things. We put it in chunks, but I really want to see how this works. So let's do that. Let's get rid of all of this. So some things that we need. We need our trait. So let's take this. Copy. We need our struct. Take this and this. And we also need display for point. And I'm guessing displays in Prelude, so we don't have to import it directly. So that's probably go above. And then where did they do the call? Did they write something with the call? No, they did not. Okay, we can try to write the call ourselves. So that point equal point, they said 1, 3. Fields are missing. Are they? Okay, had to be explicit. And then we could try to call the print line. We can do point dot outline print. Format, just in case some of this is ugly. And run. Oh, macro. And yes, I did forget that syntax. Maybe, but I think that's only if I implement debug. I don't know. Oh, look, it came out. And I have an extra parentheses for some reason. So what I was saying earlier is that the implementation looks fine for single digits, but I don't know if it works well for like double digits. Oh, no, it does. No, this works perfectly fine. I was wrong. Let me look at this again. Expand this real quick. Actually, I don't need to fully expand it. Here we go. Import, format. We have outline trait, which uses display. We have the TwoString, which calls this thing, and this returns this, which is giving us the inner portion. That has a certain length. We then find the length of the string. Length plus 4, and that seemingly gives us the top. So 1, 2, there's 2 spaces here, 2 spaces here. So yeah, this is the top, and repeating the stars. And here's where we get the second line, this portion. We have the first star, which is here, the last star, which is here, and the spaces, which is being repeated in the inside here. So that's 2 less. I count for the spacing there. Oh no, it's 2 less to account for the stars at the end because they already put it there. So that equals the same length as the top one. We then have the output, which is spaced by a star and a space, star and a space, which is here. We then have this line repeated again here. And then we have a bottom wall, which is the same as the first line here. Okay. I'm glad we read through that. I tried to do this once, and at the time I just completely failed, but I didn't know I could do it this way. But then again, this is also chapter 19. They took a very long time to tell us about this. I am curious as to why I have this extra function thing here. It's not important, but it's awkward. But in any case, it works. So moving onward. Using NewType pattern to implement external traits on external types. I have no idea what that means. In chapter 10, in the implementing a trait on a type section, we mentioned the orphan rule that states we're allowed to implement a trait on a type as long as either the trait or the type are local to our crate. It's possible to get around this restriction using the NewType pattern, which involves creating a new type in a tuple struct. We covered tuple structs in the using tuple structs without name fields to create different types section of chapter 5. The tuple struct will have one field and be a thin wrapper around the type we want to implement a trait for. Then the wrapper type is local to our crate, and we can implement the trait on the wrapper. NewType is a term that originates from the Haskell programming language. There is no runtime performance penalty for using this pattern, and the wrapper type is deleted at compile time. I'm gonna have to continue going on to see what they're actually talking about. As an example, let's say we want to implement display on vect, which the orphan rule prevents us from doing directly because the display trait and the vector type are defined outside of our crate. We can make a wrapper struct that holds an instance of vect. Then we can implement display on wrapper and use the vect value as shown in listing 19-23. Okay, that makes a lot more sense. So we couldn't implement display on vector directly because they both don't belong to us. We're not the author of them. They don't belong to our crate. But you can get around that by creating a wrapper around vector and then implementing display on that wrapper because that wrapper belongs to our crate. That makes a lot more sense. So we use standard library format, struct wrapper. It's a tuple with just a vect. So you can access it with self.0. And then we're implementing display for wrapper. So we have format, self, function, mutable, formatter, result, format result. We're writing something, writing this, and we're joining everything by commas. So we're just making it a string format of our vector. And then we can print it out here. And we created our vector, we made our wrapper, and then we printed it out. So this makes sense. That's pretty straightforward. Cargo run, and here we go. Hello world that are strings, because that's what we returned for our display for wrapper. Okay, the implementation of display uses self.0 to access the inner vector because wrapper is a tuple struct and vect is the item at index 0 in the tuple. Then we can use the functionality of the display type on wrapper. The downside to using this technique is that wrapper is a new type, so it doesn't have the methods of the value it's holding. We would have to implement all of the methods of vect directly on wrapper such that the methods delegate to self.0, which would allow us to treat wrapper exactly like vect. If we wanted the new type to have every method the inner type has, implementing the deref trait discussed in chapter 15 in the treating smart pointers like regular references with the deref trait section on the wrapper to return the inner type would be a solution. If we don't want the wrapper type to have all the inner methods of the inner type, for example, to restrict the wrapper's type behavior, we would have to implement just the methods we want manually. Okay, so that makes sense. So what they're saying here is that the downside to using this technique is that since wrapper is a new struct, it doesn't have any of the methods of vector. However, if you really wanted all of the methods of vector, you can do that by implementing the deref trait. So then, and then having everything deref to the self.0, because that is the vector, and those methods should definitely exist. However, there are cases where you would want to restrict some of the functionality, like say, make sure that this wrapper doesn't have all the functionality of the vector. In that case, then you would have to implement the methods that you wanted directly on wrapper itself, like one by one. So that makes sense. Now you know how the NewType pattern is used in relation to traits. It's also a useful pattern even when traits are not involved. Let's switch focus and look at some advanced ways to interact with Rust type system. Whew. That was enlightening and pretty heavy. I didn't know a lot of this stuff was possible, but it makes sense. It makes sense. And I'm really glad we did the wrapper thing. I legit tried to do that months ago and failed miserably. Alright, well, if you liked the video, hit like, subscribe. Outside of that, see you next time. Peace.